We will conclude our discussion of liquefaction on a positive note in terms of liquefaction mitigation. When I look at liquefaction effects, as I mentioned yesterday, I don't just look at the triggering line, which separates liquefaction effects being observed and no liquefaction effects being observed. I think about the strains and the strain potentials, and there are three areas. Areas that are scary, potential for low liquefaction, tip resistances typically less than 80, QC1N clean sand. And then we have a range where we can have cyclic mobility with limited strain potential. It may be a deformation issue, but it's typically not a major instability issue. And that's between 80 and 170 of the normalized clean sand equivalent CPT tip resistance. And once you get up to 170, you typically get up to a relative density of 80%. These are just two of the correlations I use. I use several correlations to capture epistemic uncertainty. And so therefore the goal of liquefaction mitigation, one possible goal is to densify the soil so that you move it out of the flow regime, at least toward the end of the cyclic mobility regime, and maybe hopefully in a range where you don't even have liquefaction triggered. The Japanese have been one of the leaders when it comes to ground modification. This Japanese Geotechnical Society publication, although 20 years old, it's not as old as your book, is very good guidance. It talks about principles, it talks about the methods, and then it actually gives you specific methods that, or specific techniques that employ these methods based on these principles. So this is a really good reference. I want you to have this and look at this because this is a very good way of looking at strategies to perform mitigation. Another useful document is to look at the ranges that certain soils will allow you to use certain techniques. You're not going to use particulate routes to improve silty soils. Vibratory probes work best in clean sands. So these types of things are important to consider. My general approach is look at replacement first, then structural countermeasures, vibratory densification, displacement densification, solidification and reinforcement. These are not necessarily ordered from 1 to 6, but this is deliberately listed as last and least drainage. When you think about improving the soil, you think about the 5 factors. The 5 factors are relative density, fabric, OCR, age, and time, or seismic history. And it's not that simple. So think about confining pressure, K-sigma issues, loading frequency, fines content, everything we talked about. You have to have that as a framework. The best thing to do is build it right in the first place. But if you have shallow liquefaction, another possibility is dig out the bad soil and put in the good soil. If you're going to put it in, make sure that you specify a compaction that will get to at least 80% relative density. So using ASTM D1557, which which is the modified Proctor compaction test, make sure the minimum dry unit weight you'll accept is at least 96% of the maximum dry unit weight by the modified Proctor. And don't stop there. Make sure you're adding water to the sand so you get beyond the bulking moisture content. And make sure you use vibratory compaction, because you know fabric matters as well as relative density. The Japanese standard talks about different structural countermeasures in terms of strengthening the foundation, reducing the lift of some structures. There are few things more important for a building than the foundation. A really robust foundation can cover up a lot of problems in the soil. If the soil has a weak zone and you have a very stiff foundation, it can bridge over that weak zone. So I'm a strong believer that a robust, thick, double-layer reinforcement concrete mat can do a lot to protect a structure. I've seen structures that have undergone a few centimeters of movement. I saw a structure that underwent 4 meters of movement across its building. It was greatly tilted, but nobody died in that building because it was rigid body motion and it did not take the movement of the ground and let it be expressed in the superstructure. A very good reference for you is the Japanese, which have done great work in this area, but also the New Zealand engineers have had to develop practical ways of fixing small houses where you can't spend a lot of money. And these documents are all freely available on the web. One of them is looking at a way of putting some plastic to isolate the ground deformation from the foundation and putting some reinforcement to hold things together. Again, I don't want to go through all these details. I want you to realize that these things are out there, and there are ways of reinforcing the material, putting a slip layer like a fuse, and then having a nice foundation that can tremendously help you. If the ground spreads, the structures are very sensitive to spreading. You can let that spreading happen below the foundation and not tear your building apart. The Ishihara plot, by ensuring that you have a thick enough crust over the liquefiable material, is one way of mitigating liquefaction effects in terms of ejecta, which is so damaging to a structure. So, for example, in New Zealand, they dug down to the water table where the liquefiable materials existed. They put reinforcement in the bottom. I'm a big believer in using Tensar-type geogrid reinforcement. You wouldn't build a concrete slab without steel reinforcement. Why would you build a earth fill without reinforcement? Vibratory densification is typically my favorite form of improvement because I know if I take a soil that has a relative density of 40% and I vibrate it and then check it with the cone later and now its relative density is 70%, I know it's better. If it's up to 90%, I know it's much better. Because we know vibratory densification in the right soils can increase the relative density and can also improve the fabric by giving it a more stable, resistant fabric. Realize you destroy aging and seismic history. So do not push the cone to show the owner how much you've improved the soil until you've let time go by so that you don't end up with tip resistances lower than when you first started. It takes time for those pore pressures to dissipate, for the ground to kind of settle in, and several weeks is better than a day or two. For vibratory compaction to work, sort of a rule of thumb is the hydraulic conductivity of the soil has to be at least 10 to the minus 4 centimeters per second. because then it's free draining enough. Obviously, if it's 10 to the minus 1 centimeters per second, it's much more free draining, and you will get the vibratory techniques to work. On the other hand, if you have relatively low hydraulic conductivity material, because it's a silty soil, a silty sand, then these methods will not be effective. Typically, when you have more than 20% fines, these methods start to not work well. It's one of the best ways of going if you have typical depths of improvement of 8 to 10 meters is deep dynamic compaction, because it's simple, inexpensive, and it is effective. Taking a big weight, dropping it from height, and there are guidance on what height and what weight to get some types of improvement, but you can see the improvement because of the settlement of the ground, and of course you'll do cones afterwards to prove that you've improved the ground. Vibratory probes can go deeper, and they are very effective. Here is a project at Treasure Island where a Japanese company was the best bidder for this project in the United States of America, because they tend to be very innovative and competitive when it comes to ground improvement. And they essentially had 4 I-beams with a large mass that was vibratory and just sunk these things in. In fact, this is after it's been sunk into its material. You can see the blue line is what the CPT was before improvement at several different zones. Then they did the improvement through the entire thickness, and the upper soil was improved. You can see the improvement in the CPT tip resistance, but the lower soil was not. Then you start thinking about geology, and you realize even though the CPT essentially had the same tip resistance and about the same ice of C, this is hydraulic fill built by us only about 80 years ago. It's young, it's hydraulic fill, it's pluviation through water, it's a clean sand. You can densify that with this vibratory technique. Although this has a low penetration resistance, you can't improve it because it's actually a shoal deposit where there's interlacking grains, there's little bugs that have gone through it and died. When you actually take an undisturbed specimen and look at it, you can see that it's actually a very, the matrix is very connected, very interlocked. We could not improve it because it is resistant to earthquake loading. So we had to take samples of this material and test it in the laboratory at Berkeley to prove that these soils had high site resistance ratio, and it was a problem to where when you push the cone in, they would crush and break, but under earthquake loading, they would not liquefy. So sometimes you have to supplement field testing with lab testing. In terms of displacement densification, this is where you essentially are moving the soil out of the way due to cavity expansion. You are increasing the relative density, and because you are expanding in the soil, you are increasing the lateral confining pressure, which is like increasing the OCR. The K0 goes up. Those improve cyclic resistance ratio. But again, you destroy aging and seismic history, so wait before you prove that you've improved the soil. And you do need confinement, because if it's at shallow depths, you might just push the soil up, and it might dilate if it doesn't have enough confining pressure. Stone columns are one of the most popular techniques, and you can install stone columns. You can push a cone between the stone columns afterwards to show the improvement. You cannot use these as structural elements. There was a company or two that was saying, oh, these are structural elements, they have moment resisting capability. A pile of stones has no moment resisting capability. They provide shear resistance, so relatively thin layers, when they go through the thin layer, they can provide shear resistance that will help limit the strains during an earthquake, but they cannot be modeled as structural piles. Timber piles were used in New Zealand because they were relatively cheap for improving ground for foundations for houses. I don't like them because if this liquefies, I know when there's strong shaking, there's going to be some differences between the piles and the soil. One of the best places to look for ejecta is along the pile. And so I think these might actually get a little bit of a gap in them, and then the soil that's below here will actually shoot up that gap and give you ejecta. So you need to be critical of all of these proposed techniques when they are made to save money. Compaction grouting can work. It failed in New Zealand for improving shallow liquefaction because it did not have enough confinement. In fact, the contractor was embarrassed because even after waiting a long time, the CPTs after the ground improvement had lower tip resistances than before because under low confining pressures, the soil dilated and actually became looser. So if you're going to do compaction grouting, it has to be at depth with sufficient confinement. Solidification is a very positive way. If you mix cement and soil together, you end up with soil cement. And the only issue with this is typically cost. Sometimes there's environmental concerns. People don't like the use of cement because of greenhouse gases. But jet grouting and deep soil mixing are two very useful techniques. If you're going to do deep soil mixing, as opposed to the two augers shown here, I like ones that have at least 4 or 5 augers that are all mixing things together so I get a nice panel, and then I can overlap the last auger with the first auger in the next panel and make sure I have a nice continuous element. Those are very positive. You have to do checks and tests. You pull some samples and do unconfined tests. But I found that the certainty of those being installed right is pretty straightforward. Jet grouting works well in sandy soils, but I have seen cases, I've encountered a case on a project where there was some clay at some depth. The jets hit that clay and it just balls up. And when you do cores in the jet grouting, you find balls of clay in your cement jet grouted columns. One of the greatest things you can do with deep soil mixing or jet grouting is make panels. As a former structural engineer, I like this kind of grid system because it is going to limit the strains. If we limit the earthquake-induced shear strains to less than 10 to the minus 2%, we're not going to get any pore pressure generation of any significance. If we would keep it less than about 10 to the minus 3%, 10 to the minus 1%, we are going to mitigate the liquefaction. This worked very well on the Oriental Hotel in Kobe. There was massive liquefaction all around this building, but because of this gridded system, there was no significant effects on the actual building, and there was no significant liquefaction in the ground between the panels. Sometimes structural elements are used across a weak layer to pin the top to the bottom and to provide shear resistance. That can be done across liquefiable layers as well. You need to make sure they're typically thin and you have sufficient embedment below and above so that you get good moment resisting as well as shear. Drainage. The late Professor Harry Seed is often, his name is used by saying he loved drainage, therefore he's the father of geotechnical earthquake engineering in the United States of America. I will use drainage. The late Professor Harry Seed did research on many things to gain understanding, and he did research on this, but I never heard him say in any talk that I love drainage. When you desaturate the soil, that's one thing you can do. On this project, it was cost efficient because I guess they had energy supply to just pump the water down. And if you're pumping the water down, then of course the non-saturated soil is not going to liquefy. But that's an expensive, long-term solution because you have to supply the energy to pump that water down for the rest of the design life of that structure. Some people are working at putting in gas into the soil to try to reduce the level of saturation, which increases the site resistance ratio. Some people are talking about putting bugs in the ground. The bugs go in, they maybe generate some gas, maybe they die and cement the soil together. The biggest problem you're going to have with bugs is people don't like bugs. In New Zealand, when someone mentioned, oh, we will increase the bug population that's already in the ground so that they will eat, die, and cement the soil, the environmentalists said, no way. But they're in the ground. No way. We will not allow you to manipulate bugs in the soil. So I think there are some promise with bugs and bioengineering, but I think there's some human factors and political issues that will make that a hard sell. If you're going to do drains, you need to know hydraulic conductivity. That is probably the hardest thing to know. What is the horizontal hydraulic conductivity of a highly stratified, layered, silty, sandy material? Your analysis can be no better than your understanding and characterization of hydraulic conductivity. Even if it works, it's a brittle solution. If I densify the ground and go from 40% relative density to 70% relative density, for every earthquake level of shaking, it's better. If I do my calculations right and the drains are effective, they take the water pressure away as fast as it's being generated, I'm safe. But if the earthquake's a little bit more intense or it has a pulse, and I miss that calculation, I get liquefaction. And you've wasted that investment of money. Also, even if they do work, the water is coming out, being drained away, and you're getting volumetric compression. And sometimes people don't think about the fact, if all this water is coming out of the ground, you have to make sure your drains have the capacity to take on that water, and your reservoirs have enough capacity to accept that water so that your drains don't flood the site. I am not a drainage fan. The important things to think about is you always verify the effectiveness through analysis, and then you later verify the improvement through ground investigations. There's questions about the extent of the zone, and we'll talk about that. Quality control is important, and there's very good guidance and design manuals about these different ground conditions. Because contractors are always coming up with new ideas. I'm working on a project in Myanmar where they're building a hydraulic fill on top of liquefiable materials right next to a fault that can generate a magnitude 7.5 earthquake. So we have to improve that ground. And contractors come out and say, this equipment will work. You always do a test of that, and we found out so far none of them are getting the performance that they guaranteed they would get. So if someone says, I'm going to have really good jet grounded columns, have them put them in the ground, then dig away the soil and look at them and see if they actually are 0.8 meters in diameter or whether they actually look like that. Think about environmental issues, think about cost, think about maintenance. Here's a good example. We run into this quite often. People realize if I have a building here, I want to go some distance outside of the building. If this building has no improvement, of course it's going to settle too much. Some improvement, it will settle less, but it might still be unacceptable. And so people say, well, I can't go all the way down through the entire liquefiable layer. Is it okay if I just go down 8 meters or 10 meters? Realize when you build a reinforced zone or an improved zone, let's say you use deep soil mixing or grouting or you did densification, this is now stiff. This is stiff. You left liquefiable material in here. you're going to concentrate strains there. The strains here are much higher than the distributed strains in this case, because you have that soft filling between the hard cookie top and bottom. And so this is showing you the amount of strain that accumulated in this centrifuge test. And there was a much more settlement of this building, even though the improvement was deep, than they would have thought. So go all the way through the liquefiable material, or if you cannot because it's not economical, understand you're going to get higher shear strains, higher pore pressures, and more settlement than the free field case before ground improvement. Yes, over a thinner zone, but this is a lot like the shear component as well as the volumetric component. And remember, typically the best way to say you have a liquefaction triggering issue is the CPT. So then do your improvement, if it's a densification method, and do your CPTs afterwards. But be mindful that the longer you wait, the better for getting a better characterization of the long-term effects. One last comment is use your engineering judgment. One of the best performances I saw in Japan was a tall building that did not have differential settlement next to it. Almost every tall building was on piles. The building on piles with the neutral plane below the liquefiable layer did not settle, but all the ground settled. And so all the pipes coming in and out of the building broke. They had to put in artificial ramps, or temporary ramps to get people back into the building. One person thought, I will improve the ground under my building, and then I will feather it out. I'll do partial improvement and get more and more, or less and less improvement as I go away from the building. That building didn't look like it had any differential settlement because it was a smooth transition. So ductility, those types of things are always good. Thank you. Smooth transitions. Earthquakes will always find a hard spot.